So, this is the last part of the infinite series, and here we are going to look at series representation of functions. That if a function f is infinitely differentiable, then can we represent it as a power series. So, what is the meaning of a power series? The power series is some sort of an infinite polynomial. So, here you see that this is a power series represented around the point x equal to a to the power n is the coefficient of the nth term, which is a power of x or x translated by something, the power, the nth power of that. So, here also look, if I put a equal to 0, it has become summation a n x to the power n. Now, the question here lies is, what do you mean by the convergence of such a series? Here the convergence would be that if I put a particular value of x, then you will get a series of say finite, a series of numbers, maybe positive, negative, does not matter. So, then you have to decide the convergence of that. So, if I change the x, I might get a divergence series. So, the question is that we have to find a x or an interval of x in which for every x this series would be convergent, and beyond that the series will not be convergent. So, that particular interval of x where that series would be convergent is called the radius of convergence. So, we will not go into that detail, I will refer you to the book or even your Wikipedia if you want. So, we are going to now talk about the following, that can we take a function which is infinitely differentiable and represent them in terms of a series where the coefficients are given as a derivative of a certain order. For example, there is something called the Taylor series or Taylor series of a function. So, if you have a function f, then the Taylor series of f, function f is infinitely differentiable, then it is not for every function, this is for infinitely differentiable functions. And you can just keep on differentiating to whatever order you like. See infinity functions basically. So, the kth order derivative at the point a by k factorial x minus a to the power k. So, this is called the Taylor series of f. Similarly, there is something called the Maclaurin series of f. Maclaurin series is much easier representation. This was Maclaurin was a student of Newton also, just like Taylor was. Maclaurin series is of this form. So, 0 factorial is assumed to be 1, please note this, because k is starting from 0. Because we just have to get the function f0, f of 0 a is fa. Here a is 0, a is 0, so it is just x to the power k. Sometimes it is easy to represent functions in the form of a Maclaurin series. Now, what does this essentially means? How do I find the Taylor series? See, what we know about Taylor, this fact, we know about Taylor's polynomial. So, the Taylor polynomial or of order n is given as at say time a. So, Taylor polynomial. So, Taylor polynomial is, we have already studied about Taylor polynomial earlier. If you see this course, everything is linked and everything is used. We are not doing anything out of the blue. Fn a by n factorial. So, that is the Taylor polynomial. So, what is the function? So, a function f(x) can be always represented as the Taylor's polynomial Tn x plus Rn x, the remainder term or the error term. So, what is Rn x here? Rn x is Fn plus 1 C by n plus 1, that is remainder after the nth term. So, what is C? C is something lying between x and a. Okay, I am taking x bigger than a, or it could be like this. So, C is. So, the interesting part is that if you show that this remainder can be made smaller and smaller and smaller and smaller, then this, if this remainder can be made smaller and smaller and smaller, that is if Rn x tends to 0 as n tends to infinity, then means I am making the error as n is becoming larger and larger, my error goes to 0. Then we can show, that for whatever x you choose within the radius of convergence, or for in most cases for every x, f of x can be actually written as a Taylor series. So, you can write f x as so, for this the remainder term has to go to 0 as n goes to infinity. This is a very crucial term. We will show one example of how we can show this remainder term goes to 0. Of course, if x is say very near a, and of course, if I am only looking on an interval, closed interval I, and I am only looking for those x's within that closed interval, the function is defined over that closed interval. Then over that closed interval, if fk, so fk is continuous, that will be bounded. So, basically you can bound that in if x is very near a, for that particular x as k goes to infinity, if this mod of x minus a is less than 1, then you are through, that the limit would be 0. So, Rn x is it's not how it takes a little bit of work to show that in some cases Rn x can be easily shown to be going to 0. Let us check one example. Let us take f x is equal to e to the power x. So, question is, can I represent it by a Taylor series or by a Maclaurin series? Maclaurin series is nothing but when you put a equal to 0 in the Taylor series. I understand I am not being very rigorous here, but if I want to be truly rigorous here, I think I should have spent half of the course talking about infinite series. Infinite series is a very big area, it cannot be just done in 3 lectures, but I am also learning how to give crash courses to a large group of students. Now, okay, so we are going to now try to estimate the error of this function when you write a Taylor's polynomial at around x equal to 0, and then see what happens. Now, we will consider any x in R, and let us see what we can do about the error. So, e to the power x, the Taylor polynomial at 0 can be expressed like this. So, R n x is given as e to the power c, because E x is always derivative is E x, e to the power c n plus 1 factorial into x to the power n plus 1. So, let us see what happens to e to the power. So, I am looking for now particular x, I have taken particular x in R, I am not, x is not varying here, x is fixed, my game will be played by the number n. So, x is now fixed, I am looking for this, whether for this particular given x I can write it as a series, I can remove this Rn x and I can keep on writing them. So, whether the whole thing will converge. So, I know that if this goes to infinity, I can write it, when this goes to 0, then I can write it like that. So, Ex is an increasing function. Ex is an increasing function. Now, C जो है, the C lies between 0 and x, and e to the power c lies between 1 and e to the power x. So, if x is strictly less than 0, then c is strictly 1 and e to the power x. Okay. If x is strictly less than 0, what happens? X. So, e to the power c has to, now c is lying between 0 and x. So, which means e to the power c has to be also negative, it has to be less than 1, c has to be some negative number because x is less than 0. So, x is here, 0 is here. So, c is lying here, e to the power c in this particular case has to be lesser than 1. And if x is strictly greater than 0, then, and of course, if it exists, I am not taking 0 because if it is 0, then it is 1, then I do not have to bother about this, then it is 0 0 0 0, then it is obviously I can write it as a series, but I am just bothered about strictly greater than 0 and strictly less than 0. Strictly greater than 0, then e to the power c is strictly less than e to the power x. Then what is my Rn x? Now I consider the case Rn x, I now take the mod of this. So, mod of e to the power c is anyway strictly less than 1, it is less than mod x n or n plus 1 divided by n plus 1 factorial. When x is greater than 0, then mod R n x is less than equal to in both these cases as n becomes larger and larger, x is a fixed number, and so it is n is becoming larger and larger. So, x square x whatever it is just going up. If you start from n equal to say 1, then you have x square, x cube, x 5, x 6, x 7, but the factorial, because you multiply numbers, it grows much more faster than the powers, because every time you are multiplying a bigger number. Here you are multiplying the same number. When you are doing a power, you are multiplying the same number, there you are multiplying a bigger number when you take the factorial. So, factorial is going to infinity much faster than mod x to the power n plus 1. So, mod x to the power n plus 1 means what? N plus 1 I have just multiplied x n plus 1 times, but when x is, when n is sufficiently large, then n plus 1 factorial is much larger than mod x to the power n plus 1. So, in both the cases this goes to 0 as n tends to infinity. So, my Rn x actually this term goes to 0, and which means I can make this term as small as I like, can be made less than epsilon. This is how you look at the rate of growth of functions, and that is the way you do the things. And so, here then you are able to now write e to the power x in this form 1 plus x square by 2. Now, how will you estimate the remainder? Suppose I am over an interval I am over an interval I which is a closed and bounded, and over which a continuous function, say f is a continuous or any derivative is a continuous here because it is infinitely differentiable, then it will have a bound, say over I mod fn plus 1 x less than equal to some capital M for all x in I, some interval which is a closed interval, could be closed and bounded interval, or it could be an open, I mean it could be a closed but not bounded like R. But suppose this is bounded, here also for the e to the power x case we have shown the bounds, there are bounds, right. So when x is given to me and I have this for a given x, then what do I have? I have mod Rn x is less than equal to m times, I am just taking the Maclaurin series, you can take the Taylor series, does not matter. You can write x minus a also here if you want. But what happens, whatever be your x, it does not matter, if this thing is bounded, you know that mod x to the power n plus 1 by n plus 1 factorial, does not matter what is your x, this will go to 0 as n tends to infinity by a previous discussion, which means that under this condition Rnx is going to 0 as n tends to infinity. So if you can show that this is bounded for every x in the interval, you are sure that you can write the whole thing as a Taylor series. For example, if you look at the sin x thing, so as sorry I am writing, I may sometimes making a mistake writing n goes to 0, it should be n tends to infinity always. So if you look at sin x, if you look at the sin x function, you take any, what if you take the nth derivative of it, right, okay. So it does not matter what is your nth derivative, the nth derivative would always be less than 1. So again you will have the same sort of thing and you can always write sin x as a power series. I would leave it to you for that, I will not just go in and do all these things. So you can easily do it. So with this I would like to finish my lectures on infinite series. This was just to give you a very brief idea how can functions be represented in infinite series, and a lot of things can be done after that. So after this we are going to go to multiple integrals, which we will start, and those 3 lectures would be the end of this course. So I hope you have got some idea about what is going on, may not be everything that I am speaking about, but if you get a little bit of idea, if you even get 30% of what I have been telling you, that would be enough for you. Thank you very much.